Hello, I'm Andrew Wang, and this is my Physics 22 Lab 2212 Lab 5 report. The last one, so I'm excited and let's get started. So, in the introduction, the purpose of the law was to understand Faraday's law better by dropping a bar magnet through the aluminum tube and then to collect the observation data of the drop time and compare it with the simulation model drop time. Important concepts in front was used with the Faraday's law, the Biot-Savart's law, Newton's second and third law, Ohm's law, and the magnetic force on a loop formula, and the magnetic flux on the dipole formula. To set up the experiment, the system was the bar magnet and the aluminum foil tube, and the surroundings was everything else in the surrounding universe. Assumptions made was to ignore air resistance and that gravity and the magnetic force were the only force on the magnet, applied on the magnet. To set it up, first step was to use the manometer app to determine the north direction of the bar magnet, and then the bar was dropped through aluminum foil 5 times. The measured time, then you would measure the time taken for the magnet to reach the end of the tube from the start of the tube for each of those 5 trials. These are the results. Keep in mind that the length was 0.32 meters, the width was 0.006 meters, the inner radius was about 0.03 meters, and the radius was 0.004 meters. The magnet dimensions was the dipole was 2.15 and the mass was 0.025 kilograms. And now here you could see the time measured for each trial: 1.23, 1.26, 1.29, 1.24, 1.27. You take the average of those 5 trials, that would be 1.258 seconds from the start of the tube to the end of the tube for the magnet. These are the checkpoint questions. Why can't we use a ferrous tube like a steel pipe? So the answer to that is a ferrous tube would mean that the tube is iron, meaning that it has a magnetic force that will affect the bar magnet if it's iron, so that would kind of mess the data up. The second question is, what happens to the magnet? How does it compare to a magnet falling in free space without a tube? Well, the magnet falls a lot slower than the tube because through Faraday's law, there's an induced field pushing the magnet up. So if the magnet were to fall in free space, there wouldn't be any force to act upwards against the gravity, meaning it would just fall 9.8 seconds, which is far, 9.8 seconds squared. Like that would be the acceleration, just gravity, and that'd be far quicker. For the computer simulation, this is the code I wrote. This is the code to create the tube, the foil, the magnet, and it's also the function that calculates the magnetic field of the magnet, and also the function for the magnetic flux. This is the code to simulate the magnet dropping, which is the while loop. I'm applying those calculations defined before, and this is also to visualize the simulation. This is the result. As you can see, I also graphed the velocity out, but the main thing that we're looking for is that time, the 1.247 seconds time in the tube. Now we can compare these two, right? We have 1.247 seconds from the simulation and 1.258 from the experiment. Now this slight difference, I mean, it's pretty similar, but the slight difference can be explained by the following potential sources of error. The main one would be the human error in the time measurements of the falling magnet, because I'm just using my stopwatch and my reflexes probably aren't they definitely aren't exact, so I'm probably off by a couple tenths of a second every time, and that could add up to become a pretty notable error. And also the length of the measurements of the tube could be inaccurate because I was just using a ruler and I could be off by a couple tenths of centimeter for a couple things, and that could add up too. But overall, you could tell that the results are pretty similar. The conclusion: what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So Ohm's law is I equals V over R, meaning if resistivity is reduced to almost 0, then the current would be increased drastically to almost be maximized. Now, if the current is maximized, the induced EMF will be maximized too, meaning the magnetic force induced onto the bar magnet would be a lot stronger, and the falling magnet would be a lot slower as well. What if the holes or slots were cut in the tube? How does this affect the ring currents in your model? So having more holes and slots in the tube would mean a decrease in the number of complete rings around the tube. Now with less rings, there would be a decrease in the induced current and the induced EMF, meaning that the magnet will fall a lot quicker through the tube with a weaker force acting upwards against the gravity. And yeah, that's the end of my Lab 5 presentation, and I'm just glad this is over. Have a great break, everyone.